For the coffee break, we've got Lynda Bloom and Mike McClellan. So Lynda's up next. Lynda's going to be talking about geochemistry. Lynda is a professional geoscientist and the president of Analytical Solutions. After completing her MSc in 1981, Lynda gained experience as an exploration geochemist and commercial laboratory manager. She has been president of the consulting company Analytical Solutions since 1985. She works internationally on projects ranging from stream sediment surveys to mine laboratory results. She is recognized as a world expert on sampling, assaying, and quality control, participating in over 50 short courses and workshops. She has held various management and director positions at several public companies and has a pragmatic perspective of risk and implementation. She served as the director of the PDAC for 9 years and has held numerous other volunteer and advisory board positions.
Thank you very much. Thank you all for being here today for this symposium. Much appreciated. I'm going to talk a little bit about target ranking, and what I want to do today is make sure that I put you all to sleep by putting up the periodic table. So usually what happens with any group of geologists, everybody is by now glazed over and is no longer going to pay any attention. So first thing I want to do is tell you I'm not going to talk about the periodic table. What I just want to do is remind you that a lot of people have multi-element geochemical data sitting on their hard drive somewhere, and they may never have looked at it. And all I want to do today is to ask you to go and look somewhere in some subdirectory and see if you can find that data. When I started, because Michelle unkindly said when I graduated, we would get a few elements. Maybe we would plot our copper, gold, and silver. And now we easily get 60-element packages. And one of the things that seems to happen is we sit on that data because we're a little overwhelmed. Not only are we trying to merge all those geochemical signatures with our hyperspectral and our geophysical and all the other data sets, we also have this multiple bandwidth geochemistry now, and not everybody has had the experience or been introduced to the tools to deal with that. As explorationists, really what we need to do is generate targets. And geochemistry, especially surficial geochemistry, will do a great job of that. But we all know what the risks are, and that is we only have so much money, and we need to make sure we use it effectively. So some of the projects I've seen, you may have enough money to drill 10 drill holes, but if you don't happen to prioritize your targets properly, you will run out of money before you actually get to the mine. Most important, and this is really relevant for geochemistry, but I'll say, Hernan, it also happens in geophysics. We need to eliminate testing of false anomalies. We want to drill fewer and fewer dud drill holes. Thank you very much. So what we're talking about is we really want to optimize the use of the meters drilled, and these days really save on money. So what I'm going to do is just whiz through a bunch of multi-element geochemical really case histories from my own and others, and try and give you a few clues about how you might, as I say, dig into your archives and use some data that's already there. So this is an example from BC, the BC government. So they've always been doing stream sediment surveys. This is multi-year data that's compiled, and the main objective is zinc deposits. If you were to plot the zinc data, right, that's a very good place to start. We'll throw some anomalous, we'll define anomalous as maybe the 98th percentile. We'll come up with a value of about, I think, is 168 ppm in this example, and we would actually get a group of, in this case, they're just triangles. And there's 27 triangles, and that's maybe where you could go and look for, those are the anomalous zinc values. Well, maybe we want to be a little smarter. So maybe what we could do is see if there's any effect of the secondary environment. So this is a place where I'm going to talk about a couple of times geologists who are very well trained on primary rock chemistry may not have had the training in what happens in the superficial environment and secondary weathering. So there's often a very strong correlation with iron and manganese. Copper, zinc, for example, would be co-precipitated with iron manganese hydroxides. So if you were to plot simple iron versus zinc XY plot, you might see that most of the samples actually seem to have a strong correspondence with iron. The zinc corresponds strongly with iron. And then there's these group of samples that we had plotted on the other map that are much higher in zinc relative to the amount of iron in those samples. So if we just look at those samples as opposed to including this group of samples over here that have high iron and elevated zinc, they may not be as interesting as the samples that have low iron and high zinc. And now I don't have 27 anomalous samples, I have 11. Okay, well, maybe I'm doing a better job of targeting. And then you might say, I wonder if the background zinc values change for different rock types. So for example, if I have shale units, they're really high in zinc. You know what? That's going to completely change my definition of anomalous if I can take into account both iron and geology. So for example, one of the things you could do, and here we're using geology in the sense of some regional geology that's been mapped by the Geological Survey. And if you do that again, all the points here, same iron zinc data, but now it's colored for the predominant geology of that stream sediment basin where the sample was collected. And instead, now you see a whole series of different trends. There's a, whatever color green that is, kind of a yellowy green trend and a red trend and a blue trend. And now what we want to do is we would actually go in, and it's a system called residuals. Instead of just picking the high zinc values, which is where we would start, you'd actually look at the residuals for zinc, but relative to iron, but for individual lithologies. And if you do that, you get a completely different answer from our original, right? Our original was 27 points, all sort of in the same rock type. And instead, you might get 3 anomalous values. I've got in three different lithologies and a total of 10 now what might be termed anomalous values. And of course, what you would do next is you would maybe do some ground truthing like Laurie's talking about, and you would bring in as many other data sets as possible. But this is one way to start looking through the geochemical data, and this is what I'm trying to talk about in terms of improving identification of anomalies. So some of this is as basic as an XY plot. I didn't want to get too bogged down today in all the stats for a variety of reasons, but here's just a different set of stream sediments from a project in Europe. And plotting, where am I? This is plotting copper versus iron in this quadrant. And then coloring the points that appear to be anomalous in copper relative to iron, right? So this is sort of what a residual means. It means I have this basic trend. If most of my copper values seem to increase with iron, which could be a secondary weathering effect, but I have this set of samples where copper is higher than I expect for that iron value. And what a residual will do, and I'm going to just switch to here. So what a residual would do is you would take, essentially, you would calculate the regression line through this trend, and you would measure how far the points are from that trend. And what we have done on these additional XY plots, all the same samples, and now the points in red are these, I've identified these points with the elevated copper in red, and now they just show up in my other XY plots. So it's very useful in terms of seeing if you're starting to see any kind of relationship with known deposit types. So my high copper samples also seem to have the same relationship with nickel in terms of iron. Maybe I need to start thinking along the lines of how to follow up on a possible copper-nickel a series of anomalies. One of the things that's a little different about our science than others is that we aren't just looking at the XY plots, it always has to come back to spatial distribution. Google Maps is actually a very useful tool. I'm going to show a couple of examples. This one is from Reflex, previously IO Global, and this is a plot of just arsenic values for surface samples The brighter colors are the higher arsenic values. And in this case, you would see that predominantly the higher values follow this, this valley. If you do something, again, like correct for iron, in this case using residuals, you actually find there's a different trend for arsenic that's further north, and in fact was identified the prospective lithology. The original high arsenic trend without that correction for iron was a function of landscape. So it's this idea of looking for these correlations and then trying to figure out if there's a reason why you should make corrections for them. Now, I've been saying to you, go dig out all your old data. Now, some of it's going to be a bit more challenging because we didn't always use the same method, perhaps, for the last 15 years as we were working on a project and different operators, and, well, you all know the problems. You can have different detection limits. There's a lot of different ways things change. So this is just a map showing that there's a set of cobalt data, some by with ICP after an acid digest, and the other XRF. So the XRF will be a total cobalt value relative to something that was an acid digest. Now, if you just color the cobalt points, you get this map, and it becomes very apparent that these are not these are artifacts of the data, right? This is exactly where the method change occurred. Now, you can use different leveling techniques, and there's a variety of them. And one, if you work at it, you might be able to get a map that, again, for cobalt, same data, leveled properly, and this time it has a much more meaningful result relative to the known lithologies. And these sorts of leveling problems occur perhaps more often than you think. This is one that I thought was apparent because this is a project in Mali. This is actually, this open space in here is approximately, I think, where Tabakoto is. And the area I'm showing here is almost 5 kilometers by 5 kilometers, closely spaced soil sampling. And again, color-coded for gold values. Now, what happened in year one, there was a lab was used that, for whatever reason, actually produced lower values than in year two. So the box is the survey area that was extended after the first positive set of results. But I think you can just see, on average, the backgrounds are higher and the gold values are higher. Well, in fact, the problem would be that this is not a more anomalous area than was sampled in year one. It's a problem in the difference between the labs, and you would end up with too many anomalies. So here's an example where we are looking at an area of about 10 kilometers north-south, 5 kilometers east-west, again a soil survey, and the data had been plotted in terms of, it was base metal targets, and a lot of the commodity elements of interest were plotted. It was only when you started plotting some of the other trace elements that you could find there's something not quite right. So these boundaries, again, guess what, are not geological. It signifies sampling that was done in year one, and then the grids were extended in year two outwards. What happened was, for whatever reason, from year one to year two, the analytical method, the digest was changed. So in after the fact, once you know that, you can go back and do things like look at, these are cumulative frequency plots for a variety of different elements, and you can see quite often they're very similar. So you wouldn't automatically see the differences that I was just showing, for example, for silver, if you just were looking at zinc. My problem is if you have merged those two data sets, an acarija and a stronger acid digest, and you don't know that, you might decide to use something like, let's just say you decide to use the 98th percentile, 164 ppm zinc to define what's anomalous. The problem is that, in fact, that 164 ppm may be the 98th percentile of the entire population from both years, but it's not appropriate for the analytical methods that were used in year 1 versus year 2. So in fact, what you end up doing is identifying too many anomalies in the acarija data and not enough in the strong acid data. You end up prioritizing your targets incorrectly. I have presented this before the PDAC. So Kilo Gold Mines had a project in the DRC. And to Laurie's point, I agree that it's a really good idea to have an idea of what the question is before you start trying to get involved with some of these data sets, because they are quite large and can be overwhelming. But here there were a couple of very specific questions. There's well-defined mineralization. Over here, I think they're up to 2 million ounces of gold at the Adubi deposit. There's other known artisanal workings. It's a prospective area. So they're also very limited outcrop. There's a set of, to the south, here essentially is a metasedimentary terrain and a metavolcanic terrain. So one of the questions is there a lot of transport? By using principal components analysis, which allows you to put together, in this case I think was 15 or 17 elements, and plotting those, the chemistry matched very closely with what was predicted from a little bit of ground truthing, drill holes, and geophysics, and matched well enough that one could probably have some confidence that there wasn't a lot of regional transportation. In other words, if you found an anomaly, hopefully it's not too far from, it would make a good drill target. What's interesting here is that this is accurately acarija data, and from which basically I was able to build a geology map. This happens quite often in deeply weathered terrains, and so this is something you'll see quite often done in in Africa and Australia. And again, this concept of looking at the gold distribution in the 2 different rock types and subsetting meant that we actually were able, so these are the, in this case, the probability plots for gold in the 2 different main lithologies, the metavolcanics and metasediments. And the gold is all lower in the metavolcanics. All of the work has been done in the metasediments. That's where the known mineralization is. One of the questions is, if you interpreted the gold data a little differently, would you be able to generate some targets in the metavolcanics, and perhaps there is mineralization that has not been tested previously? Also just going to point out, with this particular data set, you can really see that you can have a problem if you rely entirely on your gold data, because Stan Robinson, who did the project, did a great job of also collecting field duplicates. And the field duplicates are shown over here. So this is the average assay on the x-axis and the relative percent difference on the y-axis. And what this says is it's about plus or minus 100% reproducibility for your gold. And I don't think that's a problem with the sampling or even the assaying. I really think that's the nature of the material in this surficial environment. But it means you have to be so careful when you try to evaluate what's anomalous, and each number that you're trying to evaluate could be off by plus or minus 100%. This is an example First Quantum provided at the SCG Keystone meeting in late 2014. And this is not so much mostly what I've been talking about is, retrospective. I have some data, what could I do with it? This is an interesting concept on how to save money in their opinion. So their example is from Zambia. And they say that they collected all these different data sets, some ground truthing. You can see there's not a lot of exposure in this part of Africa. They had different geophysical data sets. And they did an interpreted lithology map. And they say that cost them $1.8 million US. They also went out and took 20,631 samples. on various soil grids. So they did 4-acid digest, 48-element ICP, geochemistry. And that cost half as much, less than half, $885,000 US, according to their figures. And by being smart about how they used all that geochemical data and looking at different multi-element relationships, and this is just a very small subset of even what they produced in, that they showed at SCG Whistler, they were able to subset a lot of these different soil samples and assign a lithology group, perhaps, to those samples. And it didn't look to me like they used fancy principal components analysis or anything like that. These are essentially XY plots for elements you might expect to help you differentiate rock types, like chromium versus vanadium, and the other one here is aluminum versus scandium. And what they did was they built a geology map, which they feel has as much value as their more traditional system of compiling all the geophysics, et cetera. You know, this obviously makes a big difference if you have local labor that is, makes it cost effective to collect soil samples and more expensive to fly in to do airborne geophysics. But it was an interesting case history that they were able to present, and they had great confidence in particular. I'm just going to try and use the cursor here to show you that this break was a redox break that they felt was most prospective for, that was where the known mineralization, the mine, fell, but also was prospective for future testing. This is an example, again, of principal components analysis, which for about 9,000 drill core samples. Now, I think a lot of this, so I've moved now from superficial to drill core. And I just want to mention this because a lot of people will have asked for maybe copper, silver, zinc, and ended up, it cost the same to do 30-element ICP. And so there's a lot of data around that people may not have looked at. We hear quite a bit about using geochemical data for geometallurgy, and I think this leads towards what you can do with it. So here's an example of plotting two principal component variables. In this case, one, for the sake of argument here, a principal component 1 versus 2, 9,000 drill core samples, and it turns out you can do a real basic discrimination of rock types. This is a skarn deposit. It's much more difficult to discriminate some of the skarns. They have highly variable geochemistry, but certainly you can look at, even with acarrhea data again, and so these are drill core. This is deeply weathered terrain. You can still make quite a few assumptions, move forward with some of the rock ID. Where this becomes useful is really, I like to think of it as checking it's not so much where you have easily identified rock types and the geochemistry just confirms it, it's actually where there are differences. And so sometimes it's a clue, for example, when you might want to go back and relog part of a hole, do more investigation of the mineralogy of that particular part of the system. And one of the big challenges with the geochemistry, especially when you're talking about 30 or 60 elements, is how do I summarize that for someone? How do I show it? And that's why I sometimes switch over to things like principal components analysis, regression analysis, because it is an opportunity to use a lot of different variables and create a new variable that can then be merged with other data. Because essentially, what we're hoping is we have more than just the geochemical data upon which to prioritize our targets. But a big part of what we need to do is visualization or communication, either with other explorationists on our team and the other people who, let's call it, own the other data sets. So here's an example of just some copper data for an area that's prospective in Argentina, prospective for copper porphyries. And this is more or less what it looks like on would look like on a map. This is more, and mostly this was ridge and spur sampling in a very remote high altitude site. But if you build a KMZ file and put that into Google Earth, you can actually move it around really nicely. You can actually see how what the mechanical dispersion looks like, for example, from the top of this hill and possibly running down the hillside. So that, especially in rugged terrain, you have a much better chance of being able to have an appropriate interpretation of your geochemical data. So it's great. It gives you an opportunity to use data you've already paid for, perhaps. It gives you an opportunity to better prioritize targets. And I just want to go through a few ways you might want to keep your eyes open as you do some of this. Again, to make sure that we can eliminate false anomalies and make sure that we will properly prioritize our targets. Garbage in, false anomalies out. Yes, you need good field descriptions. There's a lot of stuff in here about building an appropriate database and trying to, for example, identify copper done by every single different analytical method. You can always put them back together again, but if they all end up in the same column, it's much more difficult to take them apart. This idea of leveling is possible, but again, you have to know if there were different size fractions that were analyzed. You have to know if you might want to know when labs changed because perhaps accuracy and precision changed. Yes, I'm not going to give a presentation without saying quality control. Quality control. I've decided to use the little kittens for a change instead of the bullseyes because I get really tired of showing the arrows and the bullseyes to explain the difference between precision and accuracy. But you all know that. And a lot of it really is having good data management. This idea I showed already, the case history, where you don't want to mix an acarejia and a strong acid digestion. And I'm just putting in this slide to remind you that the reason is you dissolve different things, right? So the reason the acarejia and the 4-acid are different is mineralogical. Sometimes it's not possible to level because it's much more severe and complicated than simply a simple statistical manipulation. This idea I'm going to just talk about here is precision. So I showed you that example where it was plus or minus 100% for the field sampling in DRC. Just at PDC this year, Charles Baudry gave a couple of examples. He's using something called gauge R&R to try and describe the relative, let's call it the precision, the confidence you can have in a number that's reported. And he used a couple of case histories. One, soil samples collected in Brazil, and it was the target was copper nickel, and it turns out that in this particular deeply weathered terrain, the field duplicates worked out very well, and for gauge R&R, something like less than 10% for process and tolerance is very convincing, gives you a lot of confidence in your data. This was the STP data for triplicate samples taken across Lake. And for reference, here is the 10 by 10 little square that we saw from Carajás. And all of these STP analyses or enzyme later or MMI, the very weak digests and some of these other analytical methods just don't have good precision. It makes it very difficult to interpret, and it's very difficult to tell the signal from the noise. It's sort of like Laurie's problem with the size of the pixels. Especially working in Canada, we have to be very cognizant that there's a difference between mechanical and mechanical dispersion, glacial coverage. This is just a slide that summarizes some of the many different types of dispersion. And I'm going to show you this one example for relative mobility. This is a concept that not everybody picks up on right away, but was very apparent when we were working in the Yukon for Getty a million years ago. And this slide shows you that the mobility of zinc, the relative mobility for zinc in an oxidizing environment is very high relative to lead, where it's very low. and you can actually see this chemistry at work. This is Clear Lake in the Yukon, and this is a photo I took just like a really long time ago. And this white precipitate in this oxbow part of the river is literally zinc oxide. So up the hill and buried up in the hill is this, they say, an inferred resource of 7 million tons of 7.6% zinc and 1% lead. You can almost see, these were scanned photos. We didn't have digital cameras. You can almost see here the iron oxide kill zone, the Gaussian. So in here is where the lead is. It's precipitated out as the iron-bearing groundwater hits the oxygen. Everything precipitates out except the zinc that keeps going. Most statistical methods assume normal distributions. None of our data is normal, you could say. It's almost always highly skewed. So my one example, and a lot of the other statistical methods are based on regression and correlation coefficients. These 4 XY plots have these data points represented in these 4 XY plots all have exactly the same correlation coefficient. So if you only look at correlation coefficients, you will not truly understand the nature of your data distribution, either in XY or spatial. So these are some of the things I really think we can do with multi-element geochemistry. I've talked about them all, and I'm going to wrap up now. But primarily, probably the most important thing we can think about is the most important signal we can identify is a distinct lack of one, and be willing to admit when perhaps we don't. There's always a 98th percentile. There's always a number greater than the 98th percentile. It's not always a target. So thank you very much.
Lynda, we have a question online. Do you have any recommendation on how to deal with assays below detection limits? Would it be use half of limit or geostats?
It seems to me that industry standard is half the detection limit. The problem you have is when you are merging data from different sources, different years, that if you had a detection limit of 10 parts per million in historical data, and now your detection limit is 1, and you only use half the detection limit, you use that rule systematically, so you have the 10 ppm, all of a sudden you have a lot of data that are 5 ppm. Compared to your now 1 ppm detection limit, you might have a whole bunch of anomalies. So you can't do that. There's other ways you have to do that. And certainly there are some other methods of doing it, but half the detection limit is pretty common. Caveat, depending on if you're merging data.